Oh, we're on the air. Okay. So here's what so notice the units for the electric fields, units per coulomb, that's what they did here. All right, so let me show you something. So let's go back. Now be prepared. We'll do this class, we'll do this problem in class tomorrow. We'll just work on it. You guys can work on it together for about 5 or 6 minutes to start a class, get a good start on it. I probably won't solve it. We won't solve it. We won't get the answer because everyone's going to have a different one. But we'll work on that one a little bit. And what about problem number 19 here? Multiple example 3. This is again, or determine the magnitude of centripetal acceleration. F equals ma. All right. So real quick, little homework help before we jump back into the electric field here. So with this problem, number 19, the reason I'm going through this, you're going to see that the electric field problems I have on here are pretty simple, except for some other things, okay? So here's the thing. And this will be kind of a long, this one will be a little bit longer lecture thing because it's also good for Monday too. All right. So here we go. I should change this video lecture too. But anyway, so this problem is, notice what we have here. We got, suppose a single electron orbits. So if you click back here, you go, oh yeah, we talked about that problem. But this time you've got 2 protons here. And don't forget, you find the force, but F equals ma. All right, so that's not too hard. That's really not too hard because, you've got 2 charges, 2 positive 2e times the electron, which is negative e, but we're just looking at determine the magnitude. They don't want any direction here of the electrons. They want the magnitude of that acceleration that's pointing towards the middle due to the changing velocity as it's orbiting. Does that make sense? So way back chapter 4, what's Newton's? So here's the deal. So on problem 19, here's what they're looking at. Here's what they're talking about. We'll do problem 13, we'll do in class. All right, so problem 13 we'll do in class. Problem 19, here's what they're talking about. The electric force, which is equal to K, Q1, Q2 over R squared. And they've given you these because it's 2 protons times the electron. And remember, they're absolute. We're just looking at the magnitudes. They gave you this is equal to, what's Newton's second law say? Ma. What's the mass of an electron? Dinky. All right. So let's talk a little bit more about the electric field here. Oh, well, let me show you how easy these problems are now. We're going to look at this. We'll probably do 30 in class also. So we'll do 13 and 30 tomorrow in class. Right? The only thing you don't know about your homework now is this one, 32. That looks kind of funny. Well, let's just talk about it. Let's see what the slides say. All right, definition of electric field, E equals F over Q. The electric field, that a field exists. What does a field do? A field moves things. When things are in them, they start to move. Gravitational fields, electric fields, okay? Electromagnetic fields. Certain particles inside those fields will feel a force, and they will move, okay? It is the surrounding charges that create the field at a given point. So, oh gosh, what did I do? All right, so here. So the field has a magnitude of 2 newtons per kilometer. So these surrounding charges. So if I put a charge here, 18 times 10 to the negative 8, it feels a force that's going this way. All right, this is the charge. Because it's a positive charge. It wants to go away from this one and towards this one. This negative 24 would be negative 48, so Those were easy. The magnitudes of them. Look, they're given the magnitudes again. All right? And again, electric fields are also vectors. All right? Electric fields are vectors. The isolated point charge, we've already talked about that. What is the electric field? An isolated test charge of positive 15 microcoulombs is in a vacuum. The test charge is 0.2 meters away. So this guy is 15 microcoulombs. This little test charge is also 15 microcoulombs. What is the magnetic field that it feels there? Well, here's the force, and then you can just divide by this, or you can just calculate, just use Q, and just calculate KQ over R squared. And that'll be the electric field going that way for the positive charge. If it's negative, it goes the other way. So here they computed the force, and then divided by the charge, and they got that. Or you could have just said, oh, well, they changed charges only. Q naught is supposed to be 8. The slides are bad. Damn it, I always forget. Nope, sorry. Because I was going to say Q naught's got to be really small. So that slide's bad. The electric field does not depend on the test charge. There's for a point charge Q, there it is. All right, and you can add electric fields. All right, so we can find the electric field cause. So this guy is emitting an electric, E1 is emitting an electric field going this way. Q2 is emitting an electric field going this way. If I wanted to find the electric field at this point, I could just compute E1, compute E2, and notice E2 is negative, and add the two. The sum of the electric fields is what it is. Now, what they're doing is, we'll find the distance where these two electric fields will be, where the electric fields will be 0. That's kind of a tricky problem. Except here, you can do it by inspection. It worked out nicely by inspection because you wind up with this. So we got to solve for D. Well, if this is equal to 4, if we subtract 1 here, or subtract 2 here, 3 times 1, 1 squared, 4 times 1 is D, and then D is equal to 2. I mean, you could almost solve by inspection, I guess. Okay, electric fields, you can add them. All right, now we're going to talk about the parallel plate capacitor real quick, okay? Now it'll be in the next slide.